हेलो स्टूडेंट्स, आज का टॉपिक है श्मिट रीअरेंजमेंट। और स्टार्ट करने से पहले मैं थोड़ा सा तुम्हें एक छोटा सा इंट्रोडक्शन देना चाहती हूँ। हम कर रहे हैं रीअरेंजमेंट, और रीअरेंजमेंट में मैंने तुम लोग को कहा था कि रीअरेंजमेंट इज कैटेगराइज इनटू 3 ब्रॉड कैटेगरीज, जिसमें या तो इलेक्ट्रॉन डेफिशिएंसी होती है कार्बन पे, या इलेक्ट्रॉन डेफिशिएंसी होती है नाइट्रोजन पे या ऑक्सीजन पे। तो कार्बन पर जब इलेक्ट्रॉन डेफिशिएंसी होती है उससे रिलेटेड हमने 3 इंपॉर्टेंट नेम रिएक्शन की थी, पिनाकोल, वैगनर एंड डेमजानोव। और जब नाइट्रोजन पर इलेक्ट्रॉन डेफिशिएंसी क्रिएट होगी तो उससे जो रिलेटेड नेम रिएक्शंस थी वो थी बेकमैन, कर्टियस, हॉफमैन, और आज हम करेंगे श्मिट रीअरेंजमेंट। उसी तरह से जब ऑक्सीजन पर इलेक्ट्रॉन डेफिशिएंसी होती है और उस पर कोई माइग्रेशन होती है एल्काइल या अराइल ग्रुप की, तो उससे रिलेटेड भी कुछ नेम रिएक्शंस हैं जो हम आगे कवर करेंगे। तो आज का जो हमारा टॉपिक है वो है श्मिट रीअरेंजमेंट। जो इसलिए तुम्हें जो सबसे पहली बात इससे रिलेटेड याद रखनी है वो क्या, कि देयर इज इलेक्ट्रॉन डेफिशिएंसी ऑन द नाइट्रोजन एटम एंड माइग्रेशन अकर्स ऑन द इलेक्ट्रॉन डेफिशिएंट नाइट्रोजन। तो ये सबसे इम्पॉर्टेंट और सबसे पहली बात तुम्हें ध्यान रखनी है, क्योंकि इसको याद रखोगे तो आगे जो हम रिएक्शन करेंगे और जो मैकेनिज्म करेंगे उसमें हमेशा तुम्हारे दिमाग में बैठा रहेगा कि पीछे जो रीजन है वो क्या है। ठीक है, तो श्मिट रीअरेंजमेंट है इन सिंपल लैंग्वेज जब तुम किसी भी कार्बोक्सिलिक एसिड को डायरेक्टली कन्वर्ट करते हो इनटू प्राइमरी अमीन in the presence of a hydrozoic acid N3H, and specifically जो तुम acid use करते हो वो है H2SO4। So this is Schmidt rearrangement। और Schmidt rearrangement से पीछे जब हमने कर्टियस और हॉफमैन किया था, तो कर्टियस में हम लोगों ने किया था जब हम एसाइल एजाइड को कन्वर्ट कर रहे हैं into isocyanate R N डबल बॉन्ड C डबल बॉन्ड O, जिसकी फर्दर अगर हाइड्रोलिसिस करेंगे तो मिलेगा प्राइमरी अमीन। और उसी तरह से दिस वाज कर्टियस। बैकमैन में हॉफमैन में हमने किया था RCO NH2 यानी कि अमाइड को कन्वर्ट किया था इनटू प्राइमरी अमीन। तो तुम देख सकते हो कि श्मिट अगर तुम कंपेयर करो तो श्मिट, कर्टियस और हॉफमैन से कैसे डिफरेंट है। द बेसिक डिफरेंस इज दैट इन केस ऑफ कर्टियस एंड हॉफमैन you are preparing primary amine by converting the carboxylic acid into some other derivative, right? Either you are converting the carboxylic acid into a acyl azide, or you are converting the carboxylic acid into a amide. But in case of Schmidt rearrangement, why Schmidt rearrangement is better than Curtius and Hofmann? Because you can directly convert carboxylic acid into primary amines. So this is the basic difference, and this is a advantage of Schmidt rearrangement over Curtius and Hofmann. So if I take an example, for example, if I want to convert this is a carboxylic acid, and in the presence of a hydrozoic acid and H2SO4, it converts into respective primary amine. Now, as I told you in my previous videos, there are certain things that you have to keep in your mind. First, in this case also, an intramolecular mechanism is followed. That is, if we have two different type of reactants or two different type of a carboxylic acid, then they will give their respective product instead of any crossover product. Another important thing is that there is retention of configuration, which we have done earlier also. Retention of configuration will always be there. Means if it has a chiral carbon and it has a particular configuration, it will remain as such in the product also. So these two things we have done in my earlier videos also, specifically in your Beckmann rearrangement I have done in very detail, वहाँ जाकर तुम follow कर सकते हो. And now we can move to the mechanism. So the mechanism followed, I would write an important term here, concerted mechanism. Right? Now, what is the meaning of concerted mechanism? I have already done this in case of Curtius, Hofmann and Beckmann. You can follow it, but we are going to do the same thing in case of Schmidt rearrangement also. So let me show you how the concerted mechanism is followed here also. First of all, this is the carboxylic acid. So in the presence of H positive, where this H positive come from? H2SO4. H2SO4 की presence में हमें पता है क्या होगा. सबसे पहले जो O है उस पर पॉजिटिव चार्ज आया क्योंकि H पॉजिटिव जो है इसके ऑक्सीजन के लोन पेयर विल अटैक हियर, राइट. एंड फाइनली this will come out. We will have a positive charge on the carbon because H2O has come out. This will show a resonance somewhat like this also, because the lone pair on the oxygen will come here as a bond. So both of these will be in the resonance, and upon this the hydrozoic acid is going to attack. So see how the hydrozoic acid attacks. This is how you write your hydrozoic acid. Always remember, this is how you write your hydrozoic acid. And the negative charge attacks, negative charge of the nitrogen attacks on the carbon. So we have a very important molecule formed here. This attacks here. So there is an important molecule formed. I can write this like this, right? This is known as protonated acyl azide. Now this is a very important molecule here because there is going to be some changes or modification going to occur in the protonated acyl azide. Why? I told you previously, or I told you in this video also, that the most important thing that you have to keep in your mind is that there is an electron deficient nitrogen and migration is occurring on the electron deficient nitrogen. So let us see how the electron deficient nitrogen is created and migration occurs. Now in this particular case, this azide comes out because you know that this azide is a very good leaving group. So when the azide comes out, it comes out in the form of nitrogen gas. Nitrogen gas is very stable gas. So it comes out. And on this nitrogen, a very momentarily electron deficiency is created. To fill that electron deficiency, this R gets migrated here. So this lone pair of the nitrogen comes here as a bond, this azide comes out, and this R comes here. So electron deficiency is created on this nitrogen and there is a migration of alkyl group occurring on this nitrogen. So we finally get something like this, R and then N, double bond C, double bond O, and hydrogen. This nitrogen gets the positive charge so that In the next step, H positive comes out and we finally get R N double bond C double bond O. This is known as isocyanate. And you know, isocyanate upon hydrolysis gives primary amine. So that is how a carboxylic acid can be converted into a primary amine in the presence of hydrozoic acid. This is the mechanism. Now I told you it is a concerted mechanism. In this case only you can see that the removal of the leaving group, this is the leaving group and this is the migratory group. So removal of the leaving group and attachment, you can say attachment of the migratory group occurring simultaneously. When such kind of thing happens, we say it follows a concerted mechanism, right? So that is why even in case of Curtius, in case of Hofmann and Beckmann, we have discussed the same thing, concerted mechanism. And the reason is that nitrogen cannot possess the positive charge for a long time. So when the removal of leaving group is there, simultaneously the migratory group will attach to the electron deficient nitrogen, right? So this is the mechanism of Schmidt rearrangement. Now Schmidt rearrangement is shown by many molecules. It's not just that we can convert the carboxylic acid into primary amine, but we can also convert aldehydes, ketones and alcohols into some important or interesting molecules. So let us take few examples. So we can convert ketone also into something else. Now what is that something else? Let us see. So ketone can also be converted into, when we treat it with hydrozoic acid in the presence of H2SO4, what happens is that it takes up the hydrogen or H positive from H2SO4, it gets converted into this, right? Now in the next step, this bond comes here because oxygen cannot possess positive charge for a long time and carbon gets the positive charge. Now on this positively charged carbon, the hydrozoic acid attacks. This is the hydrozoic acid we have done. So the negative charge of the nitrogen attacks here and we have a case something like this. So it attacks here and it can be shown like this. Right? Now in the next step, this bond shifts here and this OH goes out. This bond shifts here and this OH comes out. So we get R N, right? And now you know what will happen. This will come out, this azide will come out. When azide will come out, this nitrogen will get electron deficiency, so one of the R will come here. So we can write it something like this. I have not distinguished these two R, both are both can be of the same kind. Both, if it is methyl, then this is also methyl, right? I have not differentiated them. Now in the next step, if I will hydrolyze, we will have here OH2 positive, double bond NR, and in the next step, finally we will have this formed, right? Do you remember where we have done this? We have done this in case of Beckmann rearrangement. So a ketone can be converted into its respective amide, you can say CO, just it was only CO here and now we have CONH, right? So that is the difference occurs when we treat it with hydrozoic acid in the presence of H2SO4. So the advantage of or application of Schmidt rearrangement when we treat ketones with hydrozoic acid is it gives a alternative synthetic route for Beckmann rearrangement. For example, if I have a case something like this, so in the presence of hydrozoic acid and H2SO4, it will give you respective lactam, either of this type or this type, and the same can be prepared by another method. If you remember, we have done Beckmann rearrangement, तो तुम्हें याद आ जाएगा कि हमने किया था ketoxymes. These are ketoxymes. ये या ये वाला. Ketoxymes को भी हम lactams में convert कर सकते हैं in the presence of H positive or any acid, and we can convert such kind of ketones also in the presence of hydrozoic acid. So मैं ये कहना चाह रही हूँ कि इस तरह के जो lactams हैं उनको बनाने के लिए हमारे पास दो सिंथेटिक रूट्स हैं. या तो तुम कीटोन्स को जो साइक्लिक कीटोन्स है उनको ट्रीट कर सकते हो हाइड्रोजोइक एसिड और H2SO4 की प्रेजेंस में, या फिर तुम कीटोक्साइम्स जो हैं उनको ट्रीट कर सकते हो H पॉजिटिव से एंड यू विल गेट द सेम थिंग. तो ये तुम्हारा बेकमैन रूट है और एक ऑल्टरनेट सिंथेटिक रूट जो है बेकमैन का वो है ये तुम्हारा Schmidt rearrangement है और Schmidt root है. So in both ways you can prepare this. Another example is of the alcohol. For example, if I have a case something like this, so in the presence of H positive, first of all the OH will come out, you know it, और कार्बन पे आ जाएगा पॉजिटिव चार्ज. Now in the presence of hydrozoic acid, or I can write it like this, HN negative N2 positive. So this negative will attack here on the carbon. We will have NH N2. Now what will happen? This will come out and one of the R will come on this nitrogen. Sorry. Right? And your final product would be an imine. Right? So when you treat alcohols with hydrozoic acid, you get an imine. When you treat ketone with hydrozoic acid, you get a amide or lactam in case of cyclic ketones. So the products are different. अगर carboxylic acid है, we get a primary amine. So that is how the reaction happens in case of Schmidt rearrangement. So this is all about Schmidt rearrangement. नेक्स्ट जो हम टॉपिक लेंगे वो है जब ऑक्सीजन पर इलेक्ट्रॉन डेफिशिएंसी होती है और उस पर होती है माइग्रेशन, तो तब हमारी कौन कौन सी नेम रिएक्शंस है इंपॉर्टेंट वो हम करेंगे इन दी नेक्स्ट वीडियो। एंड जो नाइट्रोजन पे इलेक्ट्रॉन डेफिशिएंसी थी उससे रिलेटेड हमने 4 इंपॉर्टेंट नेम रिएक्शंस खत्म की। श्मिट जो आज का टॉपिक था, कर्टियस, बेकमैन एंड हॉफमैन। So all the very best. We will meet in the next video. Thank you.